Hello students, it's Dr. Sansom. I'm going to talk to you today about using Rice tables to calculate equilibrium concentrations. This is a strategy that we're going to use when we know that a reaction will come to an equilibrium, but we don't know the equilibrium concentrations. We only know the initial concentrations. And if we know the equilibrium constant, we can still find the equilibrium concentrations. Also, if we know the equilibrium and initial concentrations, we can use that information to calculate the equilibrium constant for a reaction. We're going to talk about how to do this, which will sometimes require us to use a quadratic equation and sometimes require us to make an approximation instead. So I'm going to explain to you when we can do those things and how we carry them out. Let's begin. First, I'm going to find something. There we go. Okay. So first, just a practice problem. If we know the equilibrium constant for this reaction, 1 times 10 to the minus 14th, and we know the equilibrium concentration of H3O plus is 2 times 10 to the minus 6, we can calculate the equilibrium concentration of our hydroxide ions, because we know the expression for this is just going to be our H3O plus times our OH minus equals our K. So when we do that, we're going to end up substituting those in and calculating our concentration of OH minus is 5 times 10 to the minus 9th. When I multiply 5 times 10 to the minus 9th times 2 times 10 to the minus 6, I'm going to get 1 times 10 to the minus 14th, the equilibrium constant. So that's pretty straightforward, easy to do when our equilibrium expression only has one compound, or if we know everything except for one of them, we just solve for it. Very simple. But what if we have multiple concentrations that we want to solve for, and we only know the starting concentrations? It becomes a little bit more complicated. Thankfully, these things are related by stoichiometry, and so we can use that to our advantage to figure out what those concentrations will be. We're going to use something called a Rice table. This stands for the reaction balanced chemical equation, the initial concentrations, which we usually know, the change in concentrations, which is essentially just a shortcut for stoichiometry, and then the equilibrium concentrations, which usually are what we're solving for, but not always. We're just going to be organizing our data, what we know and what we don't know. And that's going to allow us to solve for the unknown change in concentrations and our equilibrium concentrations. So if we have this problem, we've got H2 and I2 makes 2HI. And we know initial concentrations 1 times 10 to the minus 3rd atmospheres of H2 and 2 times 10 to the minus 3rd atmospheres of I2. And we're going to allow it to reach equilibrium. When we get to equilibrium, we know the pressure of HI is 1.87 times 10 to the minus 3 atmospheres. And we're asked to calculate the K. So in this case, we know some of the equilibrium concentrations, enough information that we can figure out what the other ones are. And we're just going to substitute those equilibrium concentrations in for the K to solve for K. Okay, I'm going to share my whiteboard here. We have this reaction, H2 plus I2 makes 2HI. And that is our R for our table, the reaction. Next, we're going to put in our initial concentrations. We know that we have 1 times 10 to the minus 3 atmospheres of hydrogen and 2 times 10 to the minus 3 atmospheres of iodine. Now, in the problem, they didn't tell us anything about HI, and this is important. If they don't tell you anything about something, you need to assume that you don't have any. So we have none of that, okay? Now we're going to have this change row, and the change is going to be based on the stoichiometry. We know in this case, because we're starting with all reactants, our Q equals 0, and therefore Q is less than K, which means the reaction is going to proceed towards the products. Therefore, we're going to lose some amount of hydrogen and some amount of iodine, and we're going to gain some amount of HI. Now, the stoichiometry tells us if I lose X amount of H2, I should gain twice that much of HI. So notice as I'm making this change row in the Rice table, I'm going to use the stoichiometric coefficients here to decide the ratios of things. So this change row is really just a shortcut way of doing stoichiometry. Now, the other information they told us was that we have 1.87 times 10 to the minus 3 atmospheres of HI when we get to equilibrium. So we don't know what these equilibrium concentrations of H2 and I2 are, but we do know, because how do we get the equilibrium concentration? We start with the initial, we add the change, and we end up with the equilibrium. So in this case, we know 0 plus 2x equals 1.87 times 10 to the minus 3. That's going to allow us to solve for x. X is going to be 9.35 times 10 to the minus 4. If that's our x value, then over here we can substitute in 9.35 times 10 to the minus 4 for our x's. When we do that, we're going to get 6.5 times 10 to the minus 5 for our hydrogen, and 1.065 times 10 to the minus 3 for our iodine. And now that we know the equilibrium concentrations of all three species, we can write our K expression. It's the concentration of HI squared divided by the concentration of H2 times the concentration of I2. When I substitute these guys in, I'm going to end up getting 51 as my value of K. So I was able to find, in this case, because I had information about the equilibrium concentrations, I could find information about the equilibrium constant. Now we're going to do another practice problem, and this time we're going to have information about the equilibrium constant, but we're not going to have information about the equilibrium concentrations. So it's going to be a little bit different. Okay, in this case, I have HF. It's making H plus and F minus, and I know my K is 3.5 times 10 to the minus 4. So the question here is, if we dissolve 1 mole of HF in 1 liter of water, what will be the concentrations of all three compounds once equilibrium is established? Right now, and it's always a good practice to do this, if I substitute in my initial concentrations and find out the value of Q, it's actually 0. I don't have any of the products. And that means it's going to be going from the reactants to the products. So the reaction will move to the right. The question is how much? We don't know the equilibrium concentrations of any of these things. So we're going to use a Rice table. So we have HF, H plus, and F minus. I know my initial concentrations because they gave them to me in the problem. I'm going to use my stoichiometry to write my change row. Because it's going from left to right, I'm going to lose a certain amount of HF, that'll be minus X. And because all my coefficients are 1, I'm going to gain X amount of H plus and of F minus. So the negative sign from the HF, the positive sign for the H plus and the F minus, because those are being produced. And now I'm going to get an expression for the equilibrium concentrations. 1 minus X is going to be the concentration of HF. X is going to be the concentration of H plus and the concentration of F minus. The good news is I know the value of my equilibrium constant. So what I can do is set up my expression and substitute in what I know. X squared over 1 minus X equals 3.5 times 10 to the minus 4. Pretty straightforward. All we have to do here is solve it using, you guessed it, the quadratic equation. That's the way we're going to do it first. Then we're going to try a different way that's easier but requires some thinking. Okay, let's do quadratic equation. How do we solve this bad boy? We've got ax squared. We've got to rearrange it. So we get ax squared plus bx plus c. And then we substitute that into the quadratic equations. This is a quadratic equation here. When we do that, we get this for our rearranged equation. When we substitute it in, we get this. We end up getting 0.018 as our value of x. When you do the quadratic equation, you always get two answers, and it will always be the case in chemistry that one of those answers doesn't make sense. So this is the only one that makes sense because you wouldn't want a negative number here unless you had, the only reason you could get a negative number is if you had incorrectly decided which way the reaction would go and you wrote minus x instead of plus x back in our rice table. So you shouldn't have a negative number, and it also has to be small enough that you have enough of the initial concentration that you can subtract it and still have something left, right? It has to be physically meaningful. Okay, now I want you to pause the video if you have not done the quadratic equation in a while, and I want you to just make sure that you know how to do this. There will be problems where you have to use the quadratic equation because the other strategy I'm about to teach you is not going to work. So you need to be comfortable using the quadratic equation. So I encourage you to just pause the video and work it out for yourself here. Make sure you get the same thing that I got and you're able to solve that successfully. If you have some kind of like quadratic equation solver on your calculator, you're fine to use that. If you don't, then you have to know how to use how to do this just by algebra, okay? Okay, so now we got, when we put in our 0.018, we get 0.98 for our HF, 0.018, and 0.018 for our H plus and our F minus. And when we plug those guys back in, we are going to end up getting 3.5 times 10 to the minus 4. So we think, yes, that is a good answer. Now, this was sort of not fun. Nobody really likes the quadratic equation. I mean, maybe you do, but I don't. So can we do this a different way? It turns out we can also apply approximations. Okay, and I'm going to try to explain how we decide when we can apply an approximation. And if we apply an approximation, how do we know that it is going to be okay to do that? Okay, how do we decide after we've done it that it was a good choice for us to do that? So this is what you need to realize. First, the value of our k is very small. So even though we're starting with q equals 0, only a little bit of product is going to be formed. 3.5 times 10 to the minus 4th is a pretty small k. And that means when I'm subtracting 1 minus x, this x value is going to be pretty small. And what we're going to assume then is that 1 minus x is about the same as 1. So when we get to this point where we have this expression, we're going to ask ourselves, is this x that we're adding or subtracting, it could be added in a different situation, is it going to be small relative to the thing that we're subtracting it from? Now, this is called an approximation because you have to kind of guess. Okay, so you have to use your best judgment. How do we decide? What I normally do is I take the value of k, and then I take the value of this number that I'm subtracting x from, and I want to make sure that they're at least 3 orders of magnitude apart. That this value that I'm subtracting from the initial concentration is at least 3 orders of magnitude larger than my k value here. So in this case, we've got 1, and then we also have 3 times 10 to the minus 4. That's a 4 orders of magnitude difference. So for me, I think, yes, probably my x value is going to be small. So again, I'm comparing the concentration, the initial concentration that I'm subtracting x from, to the value of the equilibrium constant. I'm looking for at least 3 orders of magnitude difference so that I can assume that x will be small. And if that's true, then I can make this approximation that I have 1 minus x is just about the same as 1. And I end up with a much easier equation to solve. 3.5 times 10 to the minus 4 equals x squared, and that's it. So I can solve for that, and I get 0.019. And that is, if you remember, very close to what we found before when we found 0.018. So it turns out that is probably a good assumption, but we should always do a check when this happens. Our assumption was that x is going to be small relative to 1. So how do we decide if that's true? Well, our new answer that we get at the end should be within 5% of 1. So when I subtract it, I get 0.98 over here, and that is within 5% of 1. 0.98 is about the same as 1. And so this approximation is okay. We know that it'll be slightly off from the like very precise answer, but it's dramatically easier to come by. So whenever you can apply an approximation, you should apply an approximation, because the chances of you making an error if you start doing the quadratic equation go up dramatically. So applying approximation is a much better choice. Okay. That's our approximation. We got about the same thing as we did when we did it by brute force. Now, in your groups, I want you to work out this practice problem. We know the K value for the reaction. We know the initial concentrations of NOCl and NO. And as a reminder, they didn't tell us anything about Cl2, and we have to assume that we have 0 Cl2. They just told us we added these other things. That doesn't mean there's any Cl2 there, so there's nothing. Our CO2 will be at value of 0 for the initial. And we want to know what's the final partial pressure of Cl2. When we do this, we've got our initial concentrations. Again, noting it's 0 for Cl2. We'll lose 2x of our NOCl because of the stoichiometry, gain 2x of NO because of the stoichiometry, and gain 1x of Cl2. At the end, these will be our equilibrium concentrations. And what we're going to ask ourselves is this change going to be small? And if so, can we neglect x? So we can write our expression. We can plug everything in, and then we have to ask ourselves, can we neglect x? Now, the only places that we would be able to neglect x are going to be places where it's added or subtracted. And the reason is because it's going to be small relative to that thing. If it's a small number and we're multiplying it, that still matters. So we can't ever get rid of an x that's all by itself. Okay, but if the x or 2x is added or subtracted, those are ones that we could neglect. Now, in this instance, our K is 10 to the minus 8, and our initial concentrations are 10 to the minus 1. So that's 7 orders of magnitude difference, and it should be okay for us to neglect x. So we're going to remove those ones that are added and subtracted. And it ends up now that the 0.5 squared on the top and the bottom are going to cancel out, and x just equals 6.6 times 10 to the minus 8, the same as the equilibrium constant. So that is our solution for x. And that is also the concentration of chlorine at equilibrium. I want to point out, sometimes the questions will ask you different things. They might have asked you, what's the concentration of NO? Or pressure of NO, or what's the pressure of NOCl? In this case, because they asked for the pressure of Cl2, the answer is the same as x, because x is our equilibrium concentration of Cl2. But watch out, because you'll be really proud of yourself once you solve for x, and you'll think you're done. So make sure you read the question so you know whether you actually are done or whether you need to solve for something else, like plugging these guys in. Just as a check, we'll go ahead and confirm that our answer does come out to be the same when we substitute back in the value that we got this way by approximating. And it does. It doesn't even change really at all with our sig figs that we have. And so that was a good approximation to make. Okay, last thing I'd like you to do is stop and write. I'd like you to describe when you would use a rice table. What's the appropriate situation to use a rice table? And when you're using a rice table, what are the important things you need to remember? And when are you able to neglect X? We are going to use rice tables whenever we have an equilibrium reaction where there's an uncertain amount of product that's going to be formed. We know the reaction will proceed, but we don't know exactly how far because it's equilibrium instead of happening sort of completely or stoichiometrically like we have seen in the past. When we're using the rice table, the first thing we should do is write out the reaction, then anything that we know of initial or equilibrium concentrations, and then we can figure out our change row. In order to do the change row, we need to know which direction the reaction is going to go. Usually it's from left to right, but it can be from right to left, so it depends on the situation. So we need to know how Q compares to K to decide which direction the reaction is going to go. And then when we're writing our change row, we're going to use the stoichiometry, so we'll add X or add 2X, depending on what the coefficient is in the equation. To get the equilibrium row, we just add up the initial and the change rows, how much we started with, how much changed, and then we get how much we end with at the equilibrium. We are allowed to neglect x when x can be considered small relative to the amount that we're subtracting or adding it to, from or to. So if there's at least 3 orders of magnitude difference between the k, where the k is very small, compared to the initial concentrations that we're adding or subtracting from, then that means it's okay for us to neglect x. Of course, anytime we neglect x, we want to go back in and make sure that that was a good approximation and that our answer is consistent. So it shouldn't change by more than 5%. Okay, that's the end of this lecture. Thank you for listening. I hope you have a great day.